Hello, my name is Xenophon Papadimitris. I'm a professor in radiology and biomedical imaging and biomedical engineering at Yale. This interview is part of a collection of conversations with experts in medical software from academia, industry, and regulatory agencies, and is supplementary material for a Coursera class Introduction to Medical Software that will appear in the fall of 2021. Today is Steve Pieper, whom I've known for at least 15 years, maybe more. Steve is well known to anybody who does open source medical imaging software. He's part of the 3D Slicer team. He's the lead maintainer of that. Steve started out as a professor at Dartmouth and went to industry. He did a startup, he came back and now does a mixture of academic and industrial work. And we'll let him tell us a little bit more. So Steve, welcome. And I guess you should tell us a little bit more about yourself before we launch into what hopefully is a good discussion.
Well, it's great to be here and to get a chance to talk with you as always, Ineos. And I think also, as I told you, I've been very excited about this class that you've been working on because it brings together a lot of topics that are they're very important for people to know and very hard for them to learn. I personally came into this, as a computer scientist with experience in Silicon Valley, ended up getting my PhD and getting sucked into the idea of computer representations of anatomy and what you could do with them for medicine and how to make them more realistic, both by informing them from imaging and also by imposing external knowledge about how they're structured, how they move, all kinds of interesting things yet to be done about the way computers can represent humans for useful purposes. And a big part of that is that if these become useful computer programs or implementations, they can have a big impact on medicine and healthcare, and hopefully can become a routine part of care. So we're very concerned about doing all that correctly and about making the whole infrastructure robust. I guess that's kind of my main interest. And I'm, in terms of myself personally, I do really enjoy having many projects running at once with the opportunity to do prototyping and advising and still hands-on programming on stuff. So hopefully that combination of experience will give me something interesting to say about these topics that you've laid out.
So Steve, let's start with this question. All programmers have to have a set of tools, a set of libraries you trust, a set of utilities you're worried about. So how does one go assembling such a set of tools? How do you create a set of libraries that you trust on which you work on?
Well, there's the what is the adage? It's that what wisdom comes from experience, and experience comes from the lack of wisdom, because you learn when you make mistakes. And I think probably one of the biggest decisions that people are forced to make at any point in programming is whether to rely on a dependency or to implement something custom. And there are all kinds of trade-offs in that. And I think in the end, it's an art form that people just get better at, I hope, over time, based on their experience and their ability to judge other people's work in terms of whether it's going to help them. And it is entirely feasible to imagine, conceptualize a new project and minimize all dependencies. And it's very tempting to do that if you're implementing something that you feel is sort of novel and you feel like you know all the pieces, right? Write it in assembly language or C or whatever language you think you know all the pieces of, maybe to control hardware, maybe to know that you've squeezed the ultimate amount of performance out. But as everyone who's worked at that level knows, there is a whole lot of work to be done to go from a very raw, empty text buffer into a complete, full-featured, useful, and even commercially valuable, safe and effective medical product. I mean, it's a gigantic leap. So one of the things that I found, probably indispensable is collecting a curated set of dependencies that you can have some confidence in, that you're willing to commit your career effort, your mental investment to learn to do well and to understand and also to keep up with and often participate in the communities that are maintaining those. For medical devices too, these can be relationships which are commercial in nature. Though there are people who will sell you, very high level dependencies, and you can think of them as software packages, but they're really not that much. The open source license that says, hey, you can use this for anything you want, but your responsible for figuring it out on your own, that still costs you money, right? Because you have to understand the maintenance, you have to convince yourself that it's working right. Somebody else may say, here's my essentially ready to use solution that will perform to specification X, Y, and Z. You have to pay for that, but then maybe you're correct in assuming that it really will perform to those levels, or maybe your sense of testing is relaxed a little bit in that because you focus it on something else. So either way, you're making an investment in choosing a dependency that will help you achieve what you want to achieve. So to be more concrete about that, we spent a lot of time, and I know there are many ways to approach different problems, but one of the things that I've always been really interested in is what's the set of open source components that are maximally flexible in the sense that they have very few restrictions on what they require from a software licensing point of view. They don't have the GPL style reciprocal or viral licenses, so I try to avoid using those, and other licenses that are free and open, commercially friendly. I think that's really important for medical devices, because basically in the end, anything that's used in routine medical care is effectively a commercial device. So you really need to have, if you're going to use open source software, you need to make sure that it's compatible with that. And then also that are, a functional, as in they do something really useful that you're worth, you really want to have access to. And two, that have, a lifestyle or a community or a group of maintainers that are willing to keep it moving, or are amenable to doing the hard work that it takes to keep that together. So in our case, we've tried to build the 3D slicer application as kind of a unity of several key components. A key component being cross-platform C++ methodologies, how to build the software, how to use CMake to manage dependencies, how to kind of organize your code base. Then Python as a core piece of that to be able to do real-time manipulation of the data. In our case, some of the main building blocks are Qt for all the, really for the majority of operating system abstraction. And by that, I include things like networking and disks and date times and a lot of really core, features that there are other ways to do. And in fact, there's probably 18 different ways to do most of them, but most vendors will try to encourage you to use the OS level. So I mean, Mac or Windows in particular would offer you an OS level, where Qt offers you a non-OS specific layer of abstraction. And that is a very powerful piece, and not to mention that it also has a very powerful widget set, which is in some ways of secondary importance, but obviously it's still very high of importance. Then we also use extensively things at the DICOM level for medical imaging and medical communicating. And at this point, we probably have 3 different, at least, implementations that we use. 4 probably. We use GDCM and DCMTK, which are both C++ toolkits. We use PyDICOM, which is a very good DICOM toolkit in Python, but it's also augmented now by something called HiDICOM, which group of us sort of came up with to deal with things that are more complex aspects of DICOM in terms of data encoding and so forth. That doesn't really belong in the DICOM level. And then in parallel, kind of related to 3D Slicer in some ways not, is we have a whole JavaScript implementation of DICOM stuff. So DICOM for medical imaging is unfortunately something that takes more than one tool and more than one approach, because it's a very big and essential part of the project. And then 2 other big building blocks that we use extensively are ITK, the Insight Toolkit, which has image processing, image registration, segmentation, and then VTK for visualization, OpenGL abstraction, and so forth. And all of those have worked pretty much, been workhorses for now well over 10 years. I think what's happening now is that there are new opportunities to use different technologies. And again, come back to that question of choosing your dependencies and how do you want to, work with them. All the deep learning and machine learning toolkits that are available, we'd rather kind of make those optional add-ons rather than core dependencies, because especially when you're talking about hardware acceleration, there are so many complexities that come up. Visualization hardware complexities have been with us for a long time. The concept of OpenGL using a GPU has never been as smooth a thing as we'd like it to be, but it was a necessary evil. I think in some ways, avoiding that kind of deep integration of a OS or of a hardware and driver level set of dependencies, is something we want to keep our options open, because there are a lot of things changing these days.
Yeah, and I mean, staying on the concept here of abstracting the hardware in some ways, medical software often lives for a long time. I mean, we talk about using VTK. VTK goes back to 94, 93. It's in the 90s. And they have kept it going for 27, 28 years. And my hunch is going to be around for a lot longer. But part of the success of VTK is that it isolated us as programmers from the hardware. And let's stay on that topic. So you had mentioned to me yesterday when we were talking that you think of software as having three major parts, not a software, a solution as having three major parts. You have hardware, you have software, and you have data. And in people's mind, the changes and the complexity of those is often wrong compared to the way you think about them. So I'd just like you have you elaborate on that a bit.
Yeah, I can't remember where I read this first, but it stuck with me, and I think it's kind of counterintuitive, because people think of a piece of hardware being a substantial thing, and software being something you just type in and it comes and goes, and that the data, your program's running and it reads data, writes data, but the data kind of swishes into existence and disappears. But I think if you look at it from a system point of view, and from the point of view of how you actually operate over the course of years, is actually the hardware that changes the most quickly, because you get a new phone, you transfer everything over. The old phone goes to the recycler. The laptops last for, if you're lucky, 5 or 10 years, but usually it's broken before too long. But then also, so that's the case. But you think about so many core tools in software and how many pieces are still around from decades ago. You mentioned BTK, which is true, but even if people just choose the day-to-day essentials of their lives, right? Like Windows Explorer and the Start menu, right? These are pieces of software. Even though they change, the button changes. Some days it's shiny, some days it's flat, and changes over time. Those fundamental pieces of code actually do last for a long time. But when you get beyond that, really the data is the thing that persists the longest, and it's the thing you want to have persist the longest, because things that you're doing today, you don't want to have to like decode some kind of, I don't know, one-off file structure that you came up with when one afternoon, and the coding spree, and then 10 years later you have to figure out why did you decide that it should only be 10 characters long or some other thing like that. So really putting the time and effort into getting the data right is kind of fundamental to any software effort, and especially software efforts, let's say in the medical field, where those data records might be, say, the log file that described what happened during a surgical procedure, or it might be the plan that you want to be able to go back and reload into a new system after decades of experiments. And you want to, nowadays, probably one of the biggest things people want to do is implement machine learning algorithms, and they want to be able to use data that has been collected. The more data, the better, right? So you want to, and you can really see when you take that perspective, where have people made huge mistakes in the way they do their data because they didn't keep track of whether it was left or right flipped, and nobody has any way to figure it out. Or other people have made really good decisions, and data has, can kind of come from a 20-year-old system and still be meaningful to make use of. So I would say when you're, and I guess this is sort of the translation of that into practice, is that, if you think about a problem and you think about, like, say, a medical device problem that you're trying to solve, think about it from the data model first. Think about like how you're going to store the data, how often you need to access it, what format it needs to be before you start choosing a graphics card or deciding it would be fun if it was on an 8K display instead of a 4K display, because all that other stuff's going to change very rapidly.
Yeah, but the MRI of your brain will always be the same. For the most part, hopefully, of course, as we get older, those things happen. So let's just zoom in a little bit on this data. And, you bridged into it. When you talk about data, of course, a lot of what you're thinking about is data structures and how data is handled in a software over generations of software. And, you guys have seen that with the evolution of 3D Slicer, which has also been around 20 years now?
20 plus. 20
when
plus.
is 25? 25 years next year, or a couple of years from now, for sure. Yeah,
yep.
well.
Yes.
So if you think about 3D Slicer, a lot of things have changed, obviously, but some things have not.
I think something, and I think realistically,
what has not changed? Because that would be an interesting lesson, actually, as you know. Like, what's the thing that's still there? I mean, I think about the data modeling language and all of that core has been there from practically the beginning.
Well, I think the data modeling. So we use a thing called medical reality mockup language, which is an XML based, but it's really not XML based in the sense that the XML part is just kind of like an implementation detail, if you will, because what it means is that we have a scene description that says this is the state of the application, and that state of the application is, something that you can read and write to disk, and that it means handling not only kind of like the state data about where the camera is and whatnot, but also references between data sets and references to sometimes very large data sets. So a lot of the work that we did early on was kind of like knowing that the data was always going to have sort of a bulk data component and a metadata component. You needed to manage both of those. And even today, that same pattern always exists. Everybody, nowadays, it's very common. We use the other data model, from the data file perspective, we use something called an MRB, a medical reality bundle, which is just a zip file with an XML MRML file manifest and then bulk data in it. And some groups of people, for example, people working with cardiac ultrasound, where the data files are small, you'd love that. They're small. They're just like PowerPoint files that are small enough to just email around and share. We also have people who are doing, micro CT, where their data sets are in the gigabytes and growing, and they still need to consider, what disk physically am I going to keep that file on when I need to open it. So that side of the problem has kind of remained constant, and so the solution that we have worked out in terms of kind of a class hierarchy of referring to different types of data, how they get stored to disk and restored, how they get mapped between their in-memory raw data representation and their on display visualization, that display map, and then also how things communicate. So Slicer is pretty good, I think, about having a very efficient event-driven mechanism. So all these data objects emit different types of events through the observer mechanism. That's something we adopted early on from VTK, which means that they don't really talk to each other. They do event-driven communication, right? So when you, for example, have a transformation that transformation node doesn't itself know about other pieces of the system, but when the user grabs a slider and rotates that transformation node, a transformation modified event gets emitted, and then anything that's observing that is able to update itself. So if you have one MRI that's volume rendered and moves relative to another under that transform, they are indirectly coupled through this observer mechanism. And it turns out that approach has scaled very well, and it's allowed us to be pretty modular and to maintain this ability to kind of save and restore things. And I have to say that even in more recent systems that I've been involved with, one of the things I realize is that when systems aren't built from that ground perspective up, they quickly become just tangled. That people invent new managers for this kind of thing, and new, communications for keeping distance, that in sync, and you know, in my feeling, things kind of fall apart if you don't have that kind of.
I mean, it's very easy to build a small solution.
Yes.
Right. And to do these things involves paying a price at the front end. Yeah. But this allows you to scale in a way that your little solution, you know, where the object gets attached to the viewer directly and the viewer knows the buttons and all that. But in a sense, I want to zoom in on one thing. I hadn't thought about it until we started talking here, which is this concept of a state in an application. Because that gets into testing too, right? The ability of an application to keep itself in a separate state that's clearly identifiable. It's not buried into random values of random variables. It means that you can replicate where you are, and not only is it useful for your users, because obviously they can save and continue tomorrow, but even in terms of debugging, right? The ability to do testing depends on, you almost, in some ways, people think about the state as a way to create the application to make it useful, but let's switch gears a little bit and talk a little bit about testing, right?
Well, and in some ways, you know, I know there are other folks talking about, you know, quality management side of things, but you can take one concept out of quality management and apply it to software engineering. It's documented control, right? Like you need to know what the state of things is, as you say, but you also need to know when it is or isn't allowed to move from one state to another. And a lot of times people do try to diagram that and, you know, draw state machines. And I think at some level that works at the very top level of the diagram, but you quickly, you know, states are, you know, each bit is a state, right? You have gigabytes of data storage, and, you know, you have a lot of possible states to be in, so you can't draw them all. But at the highest level, you can say, and I think, you know, the more, you know, the higher you are on the risk categories, the higher concern you have about making sure that people know what's going on in the application, you may have more and more levels of state diagram that say, okay, turn the machine on, make sure that the patient is registered before you enable the button that says now turn on the X-ray beam, right? So there are state machines at that level that make a lot of sense. But when you start talking about the software, I think then you're talking, like you say, more about like testing and knowing that something is introspectable, that you can confirm that it's in a state, that you can rely on certain operations causing certain things to happen, which may be complex mathematical functions, right? This change of state isn't just a single bit changing in a vector. It can be, you know, the entire data set getting converted from Fourier space to, you know, signal space. And all these things can be, you know, well, I should say one of the things that I like, and we talked about BTK, which has been around for a while. One of the things that's been, I think, really good about BTK is the ability to interactively introspect it and to connect things together and experiment with them. You and I both spent a lot of time in Tcl interpreters doing that, and nowadays I do it every day in Python. And we can look at a, you know, you can create an instance of a class. You can connect it to another one. You can call a method on it. You can see what the result is. Being able to sort of like have that, and that's one of the things I like and try to maintain always in Slicer, is that the internals of the application are introspectable and programmable in that way, so that you can know what's going on. And if you need to, you can try what happens if I do this and what happens if I do that. These are not the same as state diagrams in the sense of exhaustively listing out, but they're, you know, for programmers, they allow you to kind of understand the scope of possibility, and then to implement things in such a way that that scope of possibility is managed, and that you can associate this set of API operations that achieves this set of results. And really, you know, although it's possible that, you know, things can get, you know, call things in the wrong order, things can have different results, but, you know, the job of the person who's actually thinking about writing these is to anticipate, right, and to, you know, and try to, and to be defensive. Say, like, you know, assume that the person who's using my API isn't going to know, or maybe they're even intentionally going to try to break it. So I need to be a little bit defensive here and write it in such a way that, you know, any unexpected condition generates the appropriate level of response. And that may be just an error message. It may be a, you know, more serious notification. or maybe even better if it handles it gracefully and does the right thing as much as possible. The worst thing, and this is just a personal gripe, but since this is a video call where I get to talk about important things, one of the things that I see a lot is asserts in C++ code, and where basically they're probably the worst thing you could do from a quality point of view, because the classical definition of an assert is that in debug mode, it aborts the program. And in release mode, it's a no-op, right? So if you're running in debug mode and trying to actually test the system, you can get to a certain spot, and then if you hit this assert, the whole program just crashes, unless you're running it in a debugger or whatever. And so that's very counterproductive, and it's annoying to me because I sometimes like to run in debug mode. But the worst thing is that if that assert really means that you should never have gotten into this state, and it's so important that you were willing to abort the program in debug mode, you certainly should not be just ignoring it in release mode, because anytime you've hit that assert, it means that the program has reached basically an out of control condition, an unknown, unpredictable, potentially dangerous position where pointers no longer point at what they're supposed to point at. And so mapping that concept of managed state and documented control to the user's experience of feeling that they understand or willing to rely on your program to accomplish, this important set of medical treatments that they're planning to do, right? That's where it hits the software architecture. Yeah. So you were asking about mistakes that when we were talking before, probably using asserts is one of the ones that I would list there.
We'll get to those in a minute. Let's stay with that. I mean, you're getting into another rabbit hole here. One of the things I like about what Slicer does, and we've tried to do similar things, and this is something that people often miss, is the concept of how the testing is done. I mean, it's nice to run unit tests where you compile against the library and you access functions and all that's nice and good, but at some level, the only testing that really you trust is the testing that uses the actual executable that the user is actually going to use, because the moment you link everything together, it's a different beast than the 5-line program that links one function and calls it once, right? The whole initialization, the whole memory. And that's something I don't see as much about. So if you talk a little bit about, the slice itself, and the whole concept of, in medical testing, we hear a lot about, well, you should test at the user's environment. In the actual part of the user environment is the actual executable, and we never really talk about that when we do a unit testing, right? It's the whole big thing.
It is interesting, and there are taxonomies, and if I try to quote them verbatim, I'll probably get them wrong. But there are, as you say, there are unit tests, and there are integration tests, and there are smoke tests, and there are ways of thinking about testing. But the one that in the end I tend to, and you can't ever do enough, right? As many tests as you write, there always should be more. So then you have to ask yourself, where do I get the most, return on my investment? And that's where I think smoke tests and unit and integration tests are probably, a worthwhile thing to do. And in particular, I consider the self-test kind of the pinnacle of that taxonomy, mainly because, as you mentioned, it uses the actual executable in the way that the user would be using it. And also, I think one of the things that's often missed in a lot of the testing strategies for, desktop and workstation software is you really don't control a lot of the variables when you build the program. When you build the program, you run it on your computer. When the user runs the program, they run it on their computer, which means their operating system, their GPU, their number of cores, their amount of memory, their disk performance, their network environment, all the things that you don't know because you're not there. So we took this approach several years ago, and I think now it's it's caught quite a few things, and the tests are still there. I mean, they go back to, I think some of them are 2013, 2011 maybe, but I think 2013 for sure. We took the concept of saying, and this was from hard experience, I have to say too, so this wasn't just a good idea, this was actually remedial in some ways, is we still do, and we'll do again probably as soon as we're back in conference mode. But we would run a course with 200 people, all we'd rent 200 computers, and they would all be set up in a big ballroom in a conference center in downtown Chicago. And we would say, okay, everybody's going to run through the same steps in this 60 slide PowerPoint presentation. And the problem, of course, with that is that, if anybody gets a crash or just even a dialog box that's not in the slides, they're going to be like, oh, you got 200 people and you're trying to run around and figure out why their computer didn't do what the slide said they should do. But at the same time, and we do less of this now. Hopefully we don't ever get back in the mode. But you'd also be fixing bugs at the last minute. You'd be like, oh, okay, these PowerPoint slides, slide 62 says that it should do this, and instead it did this other thing. So we generate a new version of the software to fix slide 62. And you need to make sure that fixing slide 62 didn't break slide 2. And so what we specifically implemented in Slicer is the concept that the self-tests are closely tied to the tutorials. So that way we can, and we also set it up so that everything that is a self-test is also a nightly regression test. So every night when we have a new version of the software it runs, it builds the packages for all the platforms, but then it uses that package to run through all the tutorial that have been turned into self-tests using the same data, using the same simulated mouse clicks on all the platforms that we support, which currently is Linux, Mac, and Windows. But it kind of covers enough territory that we've, practically speaking, can say that it's fixed the problems that we're running into, because without that kind of confidence builder, you're never really sure. And you can do it intellectually. You could say, okay, this patch fixes a bug and doesn't introduce a new bug, but we know from experience that there is no such thing as knowing for sure that it's not going to introduce a new bug.
If you're that good, you wouldn't need testing, right?
Yeah, exactly. But the testing is good too. The other thing that we try to encourage people to do is every module, the template for every module in Slicer has a button in it, for a scripted module, I should say, when we're writing stuff in Python. Every one of them has a button called reload and test. And the idea is that when you generate your template, it has a blank UI, it has a blank logic, has some place to put your data in so that it's saved and restored in the file, but it also has a template test. And what I try to encourage people to do, and sometimes it works, maybe it works better for some problems than others, but what I encourage people to do is to actually implement the test function as their place to do the prototyping. Because if the test function, closes the scene, doesn't have to exit the program, it just closes the scene, reloads a new Python script, rebuilds the GUI for that module, and then runs through the series of steps that you wanted to test anyway, then your development process is also writing your test. And that test is written in such a way that when you submit that code, it's going to be run as part of the nightly regression suite. So your self-test and your overall development are synergistic in that way. And it's very good for helping people. The things that you find with that are people develop on Windows, they don't realize it's not going to work on Mac, or they develop something that relies on something unique to their environment. So we do catch that, and then also we catch regressions from that in core libraries, where the application, in the end, that whole self-test running through the whole tutorial, in many ways depends on many layers, data read and write, proper rendering even. So there's a lot of sort of confidence associated with having a good set of tests that are close as possible to the users.
And you talked a little bit about multiple platforms, and people say, well, okay, on my medical device, I'm going to supply workstation for you. There's nothing to worry about. But even that's not true, because the network connection will change. You're going to get an operating system update. You're going to get a new monitor.
Yeah.
And the ability to verify an installation of software in the user's environment, on the user's hardware, I think it's understated. And I don't even think that the people who even the regulations don't quite go there. So it's kind of fun.
Well, and it's true. And I think this is maybe a third level thing that people don't think about until they're running a system. But I know people who do take that approach. It's like, oh, we control the workstation because it's a special workstation. But even if you don't, then the workstation controls you, right? Because 5 years down the line, that workstation is going to be obsolete, and you're going to have to convince somebody to move to a different platform, or convince yourself that if I buy the next generation, it's not going to I mean, think of all the things that can happen when you change, and I know people who've been in this, like in industry, right? Who's like, oh, we bought like 20 Dell workstations of this particular one because they guarantee to support it, or it's the long-term maintenance version, so they're always going to make sure parts are available for the next 10 years and blah blah blah. But that time frame does eventually end, and so if the product's actually good, and this gets back to the hardware software data mode, it's really expensive to maintain that kind of like legacy thing, and it's also painful, right? If you have to use a 10-year-old workstation to solve a problem that is so computationally intense, you needed this special workstation in the first place, you really want to be able to benefit from a new generation and feel that you can move forward without endangering your confidence. So yeah, again, these tests are incredibly important, and it's incredibly important to be able to recreate the environment. I mean, mostly I've been talking about mouse clicks and graphics card operations, but it can also mean as much as like simulated streams of real data, physiological data coming from a patient, or video data coming from an instrument, or anything really that replicates the real environment. The more you can do that, the more confident you're going to be, the more able you're going to be to hunt down all the inevitable headaches that come up when you actually try to do something real.
I'm not to get you down there rabbit hole here. I'm just to make a comment. We'll move on. But the amount of time you spend writing simulators for external systems sometimes.
Yeah.
Just to make sure that, because your system, of course, is not an island, right? In a medical environment, your program is a module in the user's workflow that has to connect to databases and hardware, and you're dependent on all of them. But let's leave that aside. I guess I have two more topics here. We'll end with common mistakes, but let's talk about something that seemed to be dear to you last night when we talked yesterday, when we sketched this out, which is this concept of on-site computing, remote computing, how much is running on the physical system, how much you virtualize, remote rendering, and all of that has now, it was sort of, if I may add one more thing, it may have felt academic once upon a time, but now we have streaming gaming services where all you have is a $20 gaming stick, and they're running some of the most demanding applications. I mean, games are some of the most demanding. So clearly that's not beyond the capabilities of the current hardware and the average network speed that somebody has in their home, other than some very rural areas. So where do you see that that's where we're going to be 10, 20 years down the road?
I like that environment. I agree with you that it's near and dear to my heart. It's a little bit of an obsession these days to see how to make it, kind of transition from what you call, rightly, a sort of an academic exercise or an experiment into something practical. But it really, if you think about a number of the things that, we talked about being major headaches, right? Like, oh, now I've got to run it on the user's computer where there's like maybe a different operating system I didn't expect, or maybe the user has some kind of crazy disk drive that runs out of disk space right at the wrong time. All of those things are things you would like to be able to control for. And if you can remove them from your list of headaches, you're going to be happier. I think that you mentioned the gaming services, and I think just the tide of technology and networking and whatnot, it's gotten to a point where you really do have a viable alternative to use a cloud hosted or rental computer as kind of the first option, as opposed to a fallback option. And what that really can do again, thinking about it from a medical device point of view, it's not going to be good if you need real-time streaming data from something that's close to the patient, like let's say an endoscopic video stream, maybe. Even then, maybe eventually. But for things where you're maybe doing surgery planning, maybe you're doing some complex modeling, maybe you're doing some other kind of analysis work, being able to sort of like host all that on a server that you completely control and runs in a data center in a cold room where there's no disruptions and the power is repeatable. And if you need more memory, it's just a matter of like clicking a switch on the web interface, right? All those things really do simplify some of the major concerns. They don't solve everything, but they, anything that removes major concerns is good when you're working on stuff like this. Plus, I think the other side of it, and this is one that I have to say I was a little disappointed in the cloud gaming, because I think what you said is a good reflection of what they tried to do. And and they do try to do is run somebody's console game on this cloud service and show that it's as good as their local console. But really, the opportunity is so much more, right? Because there's no reason to stop at a $500 console. You could be running a game that can only run on a $40,000 workstation that you can rent by $1 an hour, or timeshare it across multiple people. And that, or has real-time network communication with thousands of other people, right? I mean, those kind of games haven't really shown up yet. I haven't seen them, but that's, I think, going to be really, an important dimension to explore. And I think looking at it from the point of view of medical software, the corollary to that is, okay, nowadays we're seeing some really incredible, analysis routines that are available through deep learning or through other machine learning technologies that are only possible if you have 40 or 200 gigabytes of GPU memory available to you. And at the current time, and I think the prices change all the time, but it's kind of exciting to me that you can rent a 16 GPU state-of-the-art 160 gigabyte NVIDIA A100 computer from either Amazon or Google for literally tens of dollars an hour, and turn it on when you want to use it and turn it off. Now, I haven't yet seen or myself written a program that takes advantage of that to do something useful, but if that problem exists and that solution is there, I'm certainly not going to buy 16 NVIDIA GPUs and put them in my desk here. That just wouldn't be. It's just not something I plan to do. And conversely, it's not even just GPUs. You can get rental machines with 200 cores or 4 terabytes of RAM and clusters of those. So those, I think, will be really interesting things, because they would never work, or they don't work the same today as they ship a computer to the hospital model. But if you can move the data to one of these warehouse machines, run it for an hour and be done with it, turn it off, it could be really good economies of scale, could be very, very good use cases. So, the thing that is interesting about that, or at least what I like, it's in the end, when I run one of those big machines, even if it's multi-terabyte, whatever, I can run the same version of Slicer, all my regular things, my Python arrays, my VTK objects, my GPU accelerated raycasting, all those things are available just like they would be on a workstation, but they're virtualized in a way that they're available on demand. So that's, definitely something that I'm going to continue to be exploring and hopefully finding some useful applications for.
I mean, we won't talk about cybersecurity, which is the flip side of all of that, because that's like a whole kind of worms that's opening right now. But let's not go there.
Well, I will just say that, all of that, comes with a level of cybersecurity that is, state of the art, I would say, because effectively, if it's hosted on a cloud hosting machine behind the same login that, AWS uses for your credit card, or that, Google uses to maintain whatever government work those guys do, I mean, I don't think there's any, we're no second-class citizens on the cybersecurity front. We get to take advantage of all the same stuff that's available for everybody else.
We've both been in this business a while, and we've both seen mistakes, and you've learned from mistakes, and that's kind of how life goes. What have you seen? I mean, if somebody's new in this business or starting to program in a medical environment, what have you seen that you say, okay, don't do that? Like the assert you mentioned, obviously complexity is something we all try to avoid, but what else have you seen that you say, okay, don't do that, please don't?
Yeah, well, I think the thing that everybody probably has is this, I mentioned the dependency thing, but I think there's also this question that if you're going to be a professional, who's developing a system to be used for a long time that's going to work, adopt the mindset that it needs to be written clearly, it needs to be, have some of these testing mechanisms thought through, has to have, sane introspection and, this control thing. I mean, a lot of those things we've now just taught for nearly an hour, and we've given examples of all this stuff, but I do think it is hard for people to have that sink in. It's hard to get your head around what all the things are that you will ultimately want without falling into a kind of a spiral of over engineering and sort of taking on too much. And so it's like a lot of these things, you sort of like, when you see it, like, what's the right level? Well, you need the experience to know what the right level is, but there is a right level. But it's easier to see what it's done wrong. Like, it's easier to kind of see, oh, geez, this person like totally implemented this crazy level of detail abstraction and didn't write down any even hint about what it was supposed to be, or they adopted some latest and greatest craze, a language that nobody else uses, and features of that language that even the inventors weren't really quite sure they worked right. But so those are the kind of mistakes you can talk about in retrospect. I don't know if you can, other than kind of anecdotally warn against them. But I guess if I were to pick one that I think it's got a clever kind of phrase about it. But one of the things that you see a lot are domain-specific languages, right, which are academic exercises often to wrap one set of complexity with what is arguably a simpler set of complexity, simpler way of saying things. And a concrete example of it, and I don't want to pick on anyone for writing their code this way, but C++ templates can be a kind of domain-specific language where people abstract things up. And the line is from a thing called the Programmer's Devil's Dictionary, which you can find online. And I don't know who originally wrote it, but they said that a domain-specific language is a language in which code is written in one language and error messages are generated in a different language. And anytime you find yourself in that sort of a situation where you wrote one line of C++ code and got 42 pages of error messages, then you know that there's some disconnect between the level of abstraction you're working at and the problem you're really trying to solve. So I think being aware of the potential for falling into that trap, and then also trying to like say, okay, am I actually in that trap right now? Again, it's hard to kind of like lay out a set of rules that that say, don't do this, don't do that. You just have to like be aware of the kind of things that could lead to problems for you and your colleagues in the future.
And the future could be 20 years down the road for some of this code, which is also. The libraries may not be around 20 years from now. Pick them carefully.
And it is just the nature. And I don't think it's just medical. I think it's all kinds of professional software work, which is different than even the commercial, consumer level stuff. But systems get implemented, and once they work, and they're kept. We had, this company I was the CTO of a long time ago now, but it was like we came out with a product in the 90s, and it's basically the same product still on the market, same code, because it does what it does, and
it works.
Yeah.
So, Steve, thanks for taking the time.
No problem. Good to see you as always.